Exploring our cosmic neighborhood, a journey through the solar system. Here's an overview of our solar system. 1. The Sun. The central star of the solar system, comprising about 99.8% of its total mass. It is a G-type main sequence star, classified as a yellow dwarf. The Sun's energy is generated through nuclear fusion in its core, where hydrogen is converted into helium, releasing vast amounts of energy in the form of light and heat. 2. Planets. There are 8 recognized planets orbiting the Sun, divided into 2 main groups. Inner planets, terrestrial planets. Mercury, Venus, Earth, and Mars. These planets are rocky and relatively small compared to the outer planets. Outer planets, gas giants. Jupiter, Saturn, Uranus, and Neptune. These planets are much larger and composed mainly of hydrogen and helium, with thick atmospheres and no solid surfaces. 3. Dwarf planets and small bodies. In addition to the 8 planets, there are 5 recognized dwarf planets in the solar system, including Pluto, Eris, Haumea, Makemake, and Ceres. The solar system also contains numerous small bodies such as asteroids, comets, and meteoroids, which orbit the Sun and vary in size and composition. 4. Moons. Many planets and dwarf planets in the solar system have moons or natural satellites. Some of the notable moons include Earth's moon, Jupiter's Ganymede, the largest moon in the solar system, Saturn's Titan, and Neptune's Triton. 5. Asteroid belt. Located between the orbits of Mars and Jupiter, the asteroid belt is a region populated with numerous small rocky bodies called asteroids. The largest asteroid in the belt is Ceres, which is also classified as a dwarf planet. 6. Kuiper belt. Beyond the orbit of Neptune lies the Kuiper belt, a region of the solar system populated with icy bodies and dwarf planets. Pluto and Eris are among the most well-known objects in the Kuiper belt. 7. Oort cloud. The Oort cloud is a hypothetical region located far beyond the orbit of Pluto, believed to contain a vast population of icy bodies and comets. It is thought to be the source of long-period comets that occasionally enter the inner solar system. 8. Spacecraft exploration. Over the years, numerous spacecraft have been sent to explore various bodies within the solar system, providing valuable data and insights into their composition, geology, and atmospheres. Notable missions include Voyager, Cassini-Huygens, New Horizons, and the ongoing missions of rovers like Curiosity and Perseverance on Mars. The solar system is a fascinating and diverse collection of celestial objects, providing a wealth of opportunities for scientific exploration and discovery. The evolution of our solar system spans billions of years and involves various stages of formation, development, and transformation. Here's an overview of the key evolutionary stages. 1. Formation from a protostellar disk. Our solar system began as a vast cloud of gas and dust called a molecular cloud. Gravitational forces caused regions within the cloud to collapse, forming a dense core known as a protostar. As the protostar accumulated more material, it grew hotter and denser, eventually initiating nuclear fusion and becoming a star, our Sun. 2. Formation of the protostellar disk. As the protostar formed, a rotating disk of gas and dust, known as a protoplanetary disk or solar nebula, formed around it. Within this disk, dust grains collided and clumped together to form larger particles, eventually growing into planetesimals. 3. Accretion and planet formation. Over millions of years, planetesimals collided and accreted, forming larger bodies called protoplanets. These protoplanets continued to grow through further collisions and gravitational attraction, eventually forming the planets, moons, and other objects in our solar system. 4. Differentiation and planetary structure. As the planets formed, they underwent a process called differentiation, where denser materials sank to their cores, while lighter materials rose to their surfaces. This process led to the formation of layered structures within the planets, with metallic cores, rocky mantles, and in some cases, atmospheres. 5. Heavy bombardment period. Early in the solar system's history, there was a period of intense bombardment known as the Late Heavy Bombardment, where the inner planets were bombarded by leftover planetesimals and debris. This period may have played a significant role in shaping the surfaces of the inner planets and contributing to the formation of features such as impact craters. 6. Stability and long-term evolution. Over billions of years, the Solar System has evolved into its current stable configuration, with the Sun at its center and the planets orbiting in relatively stable paths. The planets continue to undergo geological, atmospheric, and orbital evolution, driven by factors such as volcanic activity, erosion, and gravitational interactions with other bodies in the Solar System. 7. Future evolution. The long-term evolution of our Solar System will continue over billions of years, with changes occurring gradually over time. Eventually, the Sun will exhaust its nuclear fuel and undergo changes such as expanding into a red giant and shedding its outer layers, potentially affecting the orbits and environments of the planets. The evolution of our Solar System is a dynamic and ongoing process, shaped by the interplay of gravitational forces, physical processes, and cosmic events over vast stretches of time. Life in Solar System. As of our current understanding, Earth is the only place in the Solar System where life, as we know it, exists. However, the search for life beyond Earth is an active area of scientific exploration, and there are several places within our Solar System where scientists believe life could potentially exist or have existed in the past. Here are some key considerations for potential life in our Solar System. 1. Mars. Mars is one of the most studied planets in the search for life beyond Earth. Although the Martian surface is inhospitable today, there is evidence that liquid water existed in the past, and there are subsurface regions where microbial life could potentially survive. Ongoing missions, such as NASA's Perseverance rover, are investigating the geology and habitability of Mars to better understand its potential for past or present life. 2. Europa, moon of Jupiter. Europa is an icy moon of Jupiter with a subsurface ocean beneath its icy crust. The ocean is kept liquid by tidal heating caused by Jupiter's gravitational forces. Scientists believe that Europa's subsurface ocean could harbor conditions suitable for life, similar to deep-sea hydrothermal vents on Earth. Future missions, such as NASA's Europa Clipper, aim to explore Europa's potential habitability further. 3. Enceladus, moon of Saturn. Enceladus is another icy moon with subsurface oceans, located around Saturn. Like Europa, the presence of liquid water beneath its icy crust raises the possibility of habitable environments. Enceladus also has geysers of water vapor and icy particles erupting from its south pole, suggesting potential hydrothermal activity and the possibility of organic molecules, which are essential building blocks for life. 4. Titan, moon of Saturn. Titan is the largest moon of Saturn and has a thick atmosphere composed mainly of nitrogen, with hydrocarbon lakes and rivers on its surface. While Titan's surface is too cold for liquid water, there is speculation about the potential for exotic forms of life that could thrive in liquid methane or ethane, which are abundant on Titan's surface. 5. Subsurface oceans on other moons. Other moons in the outer solar system, such as Ganymede, moon of Jupiter, Callisto, moon of Jupiter, and Triton, moon of Neptune, also have subsurface oceans that could potentially harbor life. While these are some of the most promising candidates for life within our solar system, the search for life beyond Earth is ongoing and continues to push the boundaries of our understanding of planetary science, astrobiology, and the potential for life in the cosmos.